It is transcribed on the fly.
Because you don't have much space.
Well, plus, this really, we have enough processing power to transcribe on the fly. I mean, that's not, it doesn't chew up that much processing power.
You've dropped 11 frames.
Yeah, quite. If you look at resources, if you look at CPU, it's
one of yours is max. Was max.
That's true. So we're fine.
So your bus is your primary limitation. You can't capture all the frames you need to capture.
That's one. Alrighty, let's get started.
Okay, guys, let's do this. Leroy Jenkins.
Okay, so last time we were already
Everybody knows that video, though.
Okay, last time we were already talking about subtracting and comparing. So if you guys want to get your homework done, you might want to pay attention a little bit. Nobody cares about the homework. Okay. Maybe grades. Okay, so subtracting and comparing is basically what we are talking about at this point. And last time we started to talk about the flags, the 4 flags that we were talking about. This part is done. Section 4 is already done. We talked about that already. The carry flag is basically the borrow flag. If you have a borrow from the most significant digit to the bit that does not exist, the carry flag will be set. Okay, so look at the carry flag as the borrow flag. They are physically the same flag. So that means if you have a subtraction or compare instruction after an addition instruction, the flag will be overwritten by the second instruction. The 0 flag has exactly the same meaning as before. Okay, which basically means if you try to construct a case to make the 0 flag become true, that's really easy. Okay, the result has to be 0. It's easy to conceptually. It's easier to use subtraction to generate a 0 than to use addition to generate a 0. Okay, yes, it is. The sign flag is exactly the same. Okay, it's just the most significant bit of the result after a subtraction. And the overflow flag is the only one that has changed significantly, because it still means the same thing. It still means the sign of the result after a subtraction does not make sense. Instead of addition, we have subtraction. So the result of a subtraction, the sign of that does not make sense. That's the overflow flag. Okay, so we talked about this already on last Thursday, and what we'll do today is to take a look at how do we interpret these particular flags. On last Thursday, we already talked about how to use the carry flag. The carry flag. Do you guys have any questions? Yep, go ahead.
No.
No? Okay. Yep.
Do you have the attendance sheet today?
No, I do not. I think at this point, people who are not, coming to the class are just shooting themselves in the foot. In fact, I would hand them a shotgun.
I'm calling Pixar. It didn't happen.
Maybe a saw, a saw barrel, shotgun. The shorter the barrel, the wider the spread. With rock salt. Yeah, that would hurt.
Yeah.
Okay, so anyway, we want to know how to interpret the flags. The borrow flag is easy because you can use it to indicate the result after a unsigned comparison. Okay, it will tell you whether the second operand is smaller than the first operand in the compare instruction. Okay. The Z flag is easy to utilize as well. It just tells you whether the 2 operands are the same or not. So what is left to do is, what about signed comparison? That's the difficult one, because no single flag is enough to tell us the result of a signed comparison. If you look at the sign flag, it doesn't work. If you look at the overflow flag, it does not work either. That's basically what we are at this point. And I just remember that I haven't done a sample program for a long time, so it's time to do some sample programs so that you guys can see how to make your own program to illustrate the points that we talk about in the class. Now, I cannot overemphasize the importance of making your own micro, example programs, just to make sure that you understand a point exactly the way it is supposed to. Okay, so that's a very important thing. But I don't want to do your homework either, so I have to be careful, what I use as the examples. So let's go ahead and take a look at the sign flag here. Okay, the sign flag after a comparison. Okay, so this is what I call a pseudo instruction, which basically means you cannot use x and y as memory operands, but we'll just pretend that we can. So in this case, the sign flag indicates whether the difference of the subtraction is negative or not. But that by itself does not tell you which number is bigger and which number is smaller. Okay? Let's go ahead and just construct two cases here. Well, there's one case right here. If x is 0 and y is negative 1, the result after the subtraction is going to have the sign flag turned on. Isn't that obvious?
Yes.
Okay, because in an instruction like this, the first operand is subtracted from the second operand. In other words, we are looking at y minus x, okay, the result of y minus x. Y is negative 1 minus x, which is 0. Don't you think the result will have the sign flag turned on? Okay, and in this case, x being 0 is greater than y, which is negative 1, when the bit pattern is interpreted signed. Is that making any sense so far? Okay. The second example is 7 versus 8. Okay, 7 is x and y is negative 8. Negative 8 minus 7 is negative 15. Negative 15 will have the most significant bit turned on because it's a negative number. So as a result,
Yeah, that should be.
I made a boo-boo here, didn't I? The sign flag should be a 1 in this case as well. That's not good. Because it doesn't show you that the sign flag all by itself is insufficient to tell you which number is larger. Oh, that's not too bad. I can give you an example where the sign flag can, let's see, we want x to be greater than y and the sign flag to be a 0. That's actually easy. Okay, let me give you a case like that. And this time I'll use a sample program to illustrate it. So we'll call this, sign being 0. Okay. I'll turn off my phone. So everything has to be done by a compare long instruction, but since I don't want to give you the answer, I'll just use compare byte instead. And let's see, 6. I want x to be greater than y, and somehow the result would have sign equal to 0. Try something like this. Let's try some negative numbers versus negative numbers. AH or AL, doesn't matter, just pick one register. So we want AL, okay, we want x to be larger than y, so we want this number to be larger than that number. Looking at 127. Okay, so this is an example that will match this case, because when we actually perform the compare instruction, x, which is negative 127, is going to be greater than y, which is in AL already, which is initialized to negative 128. So is everybody buying that x is larger than y? Okay. Mm-hmm. The question is the sign flag going to be cleared after this comparison? So we'll go ahead and finish up the program, and that's usually the way I do it, is to establish a checkpoint. What I put after the checkpoint is not going to be very important because I don't have to trace the program beyond the checkpoint, but I'll just finish the program anyway. And then we assemble the program. Oh, okay. And that's not type checking, by the way, it's just width checking. Because I use a move long to move something into AL, and AL being an 8-bit register is not going to take it. In other words, the length specified by the instruction is not consistent with the operand. And that's why the assembler can actually catch that and say, this does not make any sense. And that's the easiest kind of problem to fix because the assembler will spot it. If the assembler is spotting a problem, that means you cannot even run the program, and as a result, you will have to fix it first. LD-O S0 and 0.0, and then we'll go ahead and debug this program. Put a breakpoint on checkpoint, and well, let's not run the program. Let me put a breakpoint on line 5 so that we can actually see it step by step. So single run the program. It stops on line 5, and I can take a look at AL at this point. AL, sure enough, has a value of -128, just as expected. Okay, and this is the 8-bit representation of -128. So now we single step the program, and then we have to check the flags, and the sign flag is on. Okay, that didn't work.
You haven't done the rest of it yet. You haven't done the rest of it yet.
I don't have to do the rest of it.
Oh, never mind. I didn't see you do the single step. Never mind.
Yep. Let's see. Because in this case, I am subtracting 127 from 128. Oh, I was going in the wrong direction. Yeah, I was going in the wrong direction. Change the program. I should have gone the other direction. Okay, so IRAL, AL has -128. Is everybody convinced that 1 is greater than -128? Okay, single step, and then I can look at the flags, and this time the sign flag is off. Okay, so but what is the point that I want to prove at this point? I just want to show you that if you look at the sign flag itself, it is not sufficient to tell us which number is greater when you have signed comparison. Okay. So the example in the notes is actually incorrect, because it will actually end up with a sign being a 1 in this case. So I will have to fix my notes. But I have another example that I just went through to show you that the sign flag is not sufficient. What about the overflow flag? Yep.
So knowing if the sign flag is on or off won't tell you which of those numbers is bigger, basically, what you're saying?
Not by itself.
Not by itself.
Not by itself. The next flag is the overflow flag. Now, when you do signed comparison, the overflow flag means the result does not make any sense. So in this case, this is using 4-bit representation. So the previous example would actually work if we use a 4-bit representation. If you use a 32-bit or 16-bit or 8-bit representation, then it won't work. Okay, in this case, the 8-bit using a 4-bit representation, the overflow flag is going to be a 1 in both cases. Okay, let's double check, see if it makes sense that in both cases the overflow flag will be a 1. We are subtracting x from y. Okay, it's y minus x. And we'll go ahead and use a text editor to take a look at this. Nope, not calculator, notepad. Okay, go. Let's do the calculation. The first number is -8, and using a 4-bit representation, -8 is 1, 0, 0, 0. How do we know that? Remember that number wheel thing that we talked about earlier? Okay, so on that number wheel, 1, 0, 0, 0 can be interpreted as -8 or 8. But we choose it to use the bit pattern to represent -8 because the 1, the most significant bit, is turned on, and that means the number is negative. So we want to subtract 1 from it. Okay? And the result is quite easy. I mean, what do you think is the result? That, right? But does the sign make any sense? We are subtracting a non-negative value from a negative value, and the result is non-negative. Does it make sense? Does not make any sense, and that's why the overflow flag is a 1. So in this case, x is greater than y. Let's look at the second case. The second case has y being 7, which is 0, 1, 1, 1, and we are subtracting -1 from it. -1 is 1, 1, 1, 1, and we want to look at the result. What is the result of this? That. I don't even care whether there's a borrow in the end, okay? Because it's not a part of the equation. Because we just want to look at the overflow flag to see whether that by itself is sufficient. So in this case, what do we have? We have a positive non-negative number subtracting a negative value. We're subtracting a negative value from a non-negative value. What is the proper sign of the result?
Positive.
Should be non-negative, okay? And yet we have a negative value. So in that case, the overflow flag is going to be a 1 as well. However, in this case, x is actually less than y because -1 is less than 7. So this is enough proof to show us that the overflow flag by itself is not going to be enough to indicate which number is greater in a signed comparison. Are we doing okay so far? Okay. So now we have the L flag. Okay, there's really no such thing as the L flag. The L flag is really just a combination of the overflow flag and the sign flag. In other words, we define the L flag as this thing here. The L flag is the disjunction of OS prime, OS bar and O bar S. In other words, we are looking at the exclusive OR between the overflow flag and the sign flag. If you look at that, then it makes sense, okay? Are we okay with the definition of the L flag, which is nothing more than the exclusive OR between the overflow flag and the sign flag itself? Yep.
What do you mean by exclusive OR?
Exclusive OR means they're not the same. Okay, and it is also defined like this. If the overflow flag is a 1, I want the sign flag to be a 0. If the overflow flag is a 0, I want the sign flag to be a 1.
So overflow is a 1 sign, you want sign to be 0, so you want them reversed. You don't want them.
I want them to be different. They cannot be both be 0 or both be 1s. So are we doing okay so far with the definition of the L flag? So let's go back a little bit and see whether this is going to help us in the examples that we have already talked about. Okay. So in the first case here, okay, let's talk about the sign flag is easy. The sign flag is a 0 because it is just the most significant bit of the result. And in both cases, the overflow flag is 1. And in this case, the sign flag is a 1, and the overflow flag is a 1 as well. Right? So if I want to talk about the L flag, what would be the L flag in this case? Because they are different. And if I want to talk about the L flag here, what would that be?
0.
It would be a 0. Okay. So in this case, is it true that one number is less than the other number? Y is less than X.
Yeah.
Y is less than X because Y is -8 and X is 1. So in this case, Y is less than X is true. What about the second case? This is Y and this is x. Y is less than x is false. But that's cool. That's exactly what we want because the L flag is 0 as well. Okay? I cannot prove to you, with only examples that this is the proper way to define the L flag, or in a signed comparison, this is how you see whether a number is less than another number. Okay? Are there any questions about the definition of the L flag? Yep.
Say again how the L flag is, how do we get the L flag again?
The L flag is the result of this operation here.
What do you mean?
You mean this notation?
Yes.
We have used this notation before. The so-called multiplication is a conjunction or an and. The so-called addition is a disjunction or an or. So this is basically the same thing as O and not S, or not O or S.
You said not O or S.
Oh, not O and S, sorry. Is that okay? I mean, we have used this notation before.
Yeah, but so on a number, what represents the O, what represents the S?
What? Sorry?
On the number here?
This is our sign flag.
Oh, okay. Oh, yeah.
This is our overflow flag. And this is our L flag, which represents less than, but in a signed way. And the less than is always saying, the second operand is less than the first operand. Okay? Are we doing okay so far? Are there any questions regarding the L flag? How do we compute the L flag from the sign flag or the overflow flag? Any questions? Yep.
I have a question, but it's not about that.
No, go ahead.
Is there a reason that you're saying non-negative instead of positive? Is there?
Because 0 is neither. That's the only reason why I say it is non-negative. Because non-negative will also include 0. If I say positive, then 0 is not positive either. 0 is neither. 0 is neither positive nor negative. Yep.
We determine the top one is true because no doubt, or because I'm not basically because you came out with an even number because you subtracted a number from a small.
I don't see any even number. What do you mean by even number?
Yeah, that's all I'm saying. Basically, the signs match. The signs came out the way you wanted them to. You didn't get a negative when you needed a positive. You didn't get a positive when you needed a negative. You just told us about this.
Okay, in this case, y is -8, x is 1, and somehow the result is 7. It doesn't make any sense, right? -8 minus 1 is 7. Okay, the sign by itself does not make sense already, and that's why the overflow flag is a 1. In the second case, y is basically 7, and x is -1 because we are looking at the sign interpretation of the bit pattern, and the result in this case is actually -8. And that does not make sense either because 7 minus -1 should have been 8, but I have a result of -8. So don't even mind the actual number or the value. The sign is already wrong, and that's why the overflow flag is a 1.
What's the T and F for?
What is the T is true and F is false?
Okay, so then I should be asking, what makes the first one true and the second one false?
Because this is why -8 is less than 1. That's why y is less than x is true.
That's what you're determining if it's true or not.
Yes.
That's what you're saying. Okay.
Yep. In the second case, y is 7 and x is -1, so y is less than x is false.
Okay, all right. So are we gonna have to eventually determine if they're true or false by comparing x and y? Is that what you're teaching?
I'm saying that the overflow flag by itself is not sufficient to tell us which number is larger, but the L flag is. the L flag being the exclusive OR between the O flag and the S flag, will tell us in a signed interpretation which number is larger.
So on all the flags, the L flag is the only one we can look at to figure out if the Y is bigger than the X or the X is bigger than the Y.
It can only tell us whether X is greater than. Okay, let me see.
So the L flag is what we-
It will only tell us, whether it can only compare this way.
Oh, only can compare Y is less than X.
Yep, it can only tell us whether Y is less than X. Sorry?
The L flag is the only one we can use to look at for that information to figure out Y is less than X.
Yes.
Okay.
Yep. Yep. Go ahead.
I was just going to, for clarification, say, so you will not have an L flag set if both your S and O flag is 1 or your S and O flag are 0. Right?
Correct.
Okay.
Yeah, that is correct. Yep.
So are you gonna go over the other signs?
The unsigned, we talked about that already. The borrow flag or the carry flag will tell us the answer for that, for unsigned comparison. Okay. Any other questions about this? Well, let me just work this out, just one more step, okay? To make it more confusing. So I'm going to use exactly the same two cases, except this time I don't care about the sign flag or the overflow flag because I'm going to look at everything in an unsigned way. Okay, I'm going to interpret everything unsigned. So some of these numbers will also be changed because I'm not looking at things from a signed perspective. What is the value of 1000 in binary in an unsigned interpretation?
8.
That's 8, okay. And what is 0111? It's still 7. And in this case, what is 1111? Okay, that's 15. And what is 1000? That's 8. Okay, very good. What about the borrow flag? Is there a borrow here? What is the final borrow?
0.
Okay, there's no borrow. Ah,
Oh, no.
okay. Getting into the wrong mode. Okay, what about this? Do we have a borrow?
Yeah.
We have a borrow. Okay. So in this case, Y is less than X is it true or is it false? It is false, and the carry flag or the borrow flag is 0. In this case, Y is less than X is true, okay, and the borrow flag is 1. Now this is by no means a proof to show you that the borrow flag is in fact the indicator of whether Y is less than X in a unsigned comparison, but it is an illustration to show you that we can use exactly the same bit patterns. Okay, I'm using exactly the same bit patterns and using the same subtraction, but by looking at the bit patterns using signed versus unsigned and looking at different flags, I can come up with different answers. Because over here, the first two cases, over here, I'm only focused on the signed interpretation. I don't even care about the borrow flag because I know the borrow flag is useless for signed comparison. If I only look at the signed flag and the overflow flag and also the L flag, which is a combination of the two, the L flag is sufficient to tell us the result of the comparison. It tells us whether Y is less than X or not in a signed interpretation. But I can take exactly the same bit patterns and do the same subtraction, but this time I only focus on the borrow flag. And this time, when I look at things from the unsigned perspective, the borrow flag will tell us which number is bigger, okay, or whether Y is less than X. Is that doing okay? Concept-wise, is that okay? Yep.
Oh, no,
You.
so you use the borrow flag, kind of like the L flag too, if you wanted to, and be able to figure out if Y is less than X, or they can't use it both ways.
B, or the borrow flag or the carry flag is only for unsigned comparison, and the L flag, which is a combination of the sign and the overflow flag, is only useful for signed comparison. Okay, so the bigger question, I think the bigger question is, does everybody understand why 1000 as a 4-bit bit pattern can both be representing -8 and also 8?
Yes.
Okay, it's not really representing both values at the same time. You, as a programmer, has to decide how to look at the bit pattern. Okay, so that's why this is the big difference between programming in C versus programming in assembly language. Because in C, once you tell the compiler and say X is assigned whatever, can be assigned char, can be assigned short int, can be assigned int, can be assigned long int, can be assigned long int, it doesn't matter. Because after that, whenever you compare X to something else, the compiler knows that it has to use the signed comparison. Okay, and it will do everything else correctly. But when you're doing assembly language programming, there is no such thing. The bit pattern 1000 has no inherent signedness to it. Okay, you can look at it signed, you can look at it unsigned. It is nothing more than 4 bits. Okay, it is up to the flags that shows you the result of a comparison. Yep.
I was wondering if we were to look on the eflags command or IR eflags. Where is the L flag in that?
It does not have an L flag, and that's why I use my own command, flags that will actually show you the combination of the two. If you want to look at the L flag, okay, let me just kind of switch back to the to this part here. So in this case, I see the overflow flag. I don't see the sign flag, which means if I had an L flag, it would have been a 1. If I look at the previous case, let's see here, I only have the sign flag without the overflow flag, so that means the L flag would be turned on as well, because as long as one is a 0, the other one is a 1, doesn't matter which one, as long as they're not the same, the L flag is on. Yep.
So in the future, is the L flag something we'll be actually able to access, or is that something we'll have to generate when we want it?
That's a good question. Okay, that's a good question because there's really no such thing as the L flag in the processor. Okay, because the processor computes the exclusive OR between those two on the fly. But there is a JL instruction. In other words, it makes use of the S flag and the O flag together as if there is a flag called the L flag. So that's why I name it L flag, so that the name of the flag will match the instructions that we'll talk about later, the conditional branch instructions. But that's moving a little bit ahead of time. Yep.
So it doesn't store it as the L flag, but it kind of treats it as the L flag, some computation.
The L flag can be computed by the sign and also the overflow flag, so that's why there's no need to store it. So it is not stored anywhere, but we can just imagine there is an L flag to make it easier for us to interpret the result after a compare instruction.
But there's built-in commands to deal with an L flag, like the processor sort of expects an L flag.
The processor can look at the sign and the overflow flag together, and on the fly interpret it as an L flag. But it does not store. There's no storage for an L flag. Okay. Are there any other questions about the flags? Yep.
Can I see that example one more time?
So this is a useful example because as confusing as it seems, it does describe the main differences between how we look at things from the C perspective, which is okay, everything is easy, as opposed to the assembly programming perspective, because we are looking at bit patterns. How you want to interpret the bit pattern is up to you. And not only that, the only time when, whether a number is signed or not is, when you do comparison. When you do comparison, you basically have to look at the sign or the overflow flag when you're dealing with signed interpretation, or you have to look at the borrow flag or the carry flag when you're looking at things from the unsigned perspective. So you choose the flags that you pay attention to in order to determine whether it is signed or unsigned. Okay? There's no such thing as data type in assembly language programming. Okay? Are there any questions at this point? Yep.
So if the borrow is 0, it means unsigned.
No. When a borrow is 0, that means you are looking at things from the unsigned perspective. And when you look at borrow, okay, whether it's 0 or not doesn't matter. When you look at the carry flag, otherwise known as the borrow flag, that means you are interpreting things unsigned. When the borrow flag is a 0, that means y is less than x. When the borrow flag is, I'll take it back. When the borrow flag is a 1, y is less than x. When the borrow flag is a 0, y is not less than x. It can be the same.
Oh, confusion.
Confusion?
Can you repeat that again? So that was.
How about I sum it up like this?
Alright.
And people who know me know that my summary usually is very concise. B equals 1 if and only if y is less than x in and using the unsigned interpretation. L equals 1 if and only if y is less than x using the signed interpretation. So 2 sentences sums up the whole thing. Does everybody understand the differences between if, only if, and if and only if? Yes? No? Kind of? Maybe? Never heard of that? Yep.
Yes, but there are other ways to make b equal 1. Yes, but there are other ways to make b equal 1, so saying if and only if there is wrong.
Well, but in the case of comparison, this is the only way you can make b equal to 1. Using the signed, unsigned interpretation is when y is less than x. Okay. When we consider the flags after computing y minus x, how's that? I think that really helps to clear up everything. Or not? Is that okay? Yep.
How do you know if they're, probably said this, but you're the one, the programmer is the one that says if they're signed or unsigned, right? Are you
Okay, I can give you one example, okay? In my program, I reserve 4 bytes for a value, okay? So 4 bytes means I have 32 bits. Now, if I want to use the 32 bits to represent my bank balance, okay, do you think I should be using the signed interpretation or the unsigned interpretation?
unsigned?
Well, when you're talking about bank balance,
negative.
it is unsigned because I cannot have a negative balance. Okay? What about what?
I have a negative balance right now at the bank.
You cannot have a negative balance because if you try to draw money from your bank and there's not enough money, it won't happen. It just won't happen.
Want to bet? I can show you a negative statement.
Okay. What about, let's see, let's think of something that can be negative. Okay, temperature. Okay, if I look at temperature, if I want to use let's say 1 byte, okay, which to store temperature in Fahrenheit, okay, or Celsius.
We're computer scientists.
Kelvin.
Use Celsius or Kelvin.
Okay. Now, in the case of Kelvin, it is going to be signed or unsigned.
Unsigned.
It's going to be unsigned because you cannot get a negative value when you measure temperature in Kelvin. But when you measure temperature in Celsius or in degrees Fahrenheit, then they can be positive or negative. So whether you should be looking at things from a signed perspective or unsigned perspective depends on what it is really storing. What is the value corresponding to? Is it corresponding to something that can never go negative, or is it corresponding to something that can go either positive or negative?
So it depends on what you're using it for, basically.
Yes, and as a programmer, you determine that.
So it depends on what you're using it for, if that value is being negative or positive.
Yes, or it depends on how I make the homework assignment.
So they're telling you signed or signed, if we have to do something, or we have to figure out the L value or the borrow value, depending on unsigned or signed. Then you can't use borrow. You said you can't use borrow with unsigned or signed.
Okay, let me put it this way. If you have 2 temperatures stored in 2 bytes, okay, and you know the temperatures are stored in kelvins, okay, then after a comparison to see whether this temperature, how does this temperature compare to the other one, you only need to pay attention to, no, which flag? Which flag do you pay attention to?
What temperature?
Kelvin, okay, I'm storing my temperatures in kelvins. And using either 16-bit or 32-bit, doesn't matter. And I want to compare. Okay, which flag should I pay attention to after a comparison? The borrow flag, very good. Okay, if I store temperatures, in the regular way in the United States, we do it in degrees Fahrenheit, right? So if I want to compare two temperatures in degrees Fahrenheit, which flag or flags should I pay attention to?
The L flag.
The S and the O flag. Or if you want to combine the two to the L flag, that's fine as well. So that's how you choose, which flag to pay attention to. Now we have not talked about any instructions that pay attention to the flags. Okay, other than the add with borrow, add with carry, and the subtract with borrow, we have not really talked about any other instructions that will utilize the flags that we have been talking about so far. So that's basically what we'll talk about next, are the instructions that will do that. Yep.
This is actually a tad off topic, but what's the command for subtract with carry? Is it SUC?
Subtract with borrow that's a good question. I cannot remember.
Because add with carry is
GFGI.
ABC, but with the subtraction be SUC.
That's a good question. Let me give it a try. Okay, so we want to find out whether we can do a subtract with carry byte, or whether we can do a subtract with borrow byte. Right? Those are the two alternatives.
Yeah. And then I'll tell you which one's possible, because say the other one's not.
So subtract with carry is not accepted, but subtract with borrow is accepted.
All right.
So SBB, whatever, is the correct one. Good question. I could not remember which one it was. Yay. So are we doing okay so far with all the flags? Shall we move on to instructions that actually make use of them? Yep.
Can you do that in a sample program?
Do it what?
A subtraction with borrow?
Yes, we can do that.
Thank you.
And to do that, let's go ahead and do a somewhat tricky one too. So that if you use the wrong one, it won't work correctly. So we want to look at a 16-bit subtraction, and we break it up into two 8-bit subtractions. And the best one to do is the one that will generate a borrow to the next one, such as something like this. So we have two 16-bit numbers. The first one is 00000001, 00000000, and the second one can be as simple as that, right? Because in the proper subtraction, okay, if this is done correctly, it is pretty easy. You just have zeros all the way up to here, and these will all be ones. Okay? But if you do it wrong and do not forget to use subtract with borrow, then you will end up with a 1 here, and the result will be incorrect. Okay, so let's go ahead and make this happen. So subtract with borrow. Dot next. And let's see, this is move word into, say, AX. That's the first number, okay? There are several ways to do it. One way is to use the binary representation, which is it 0B?
Yeah.
And then 1, and then followed by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. So that's one way to represent this particular bit pattern. And then what we want to do is to use two subtraction instructions, one to deal with this column, and one to deal with this column here. The first one would be a regular subtraction, byte, and we'll be subtracting 1, or if you prefer, we can be redundant and have all the leading zeros, from the least significant byte of AX. What is that?
AL.
Okay, very good. And then we have a subtract with borrow byte, and that's going to be all zeros, 0B, and then 8 zeros from AL as well.
Wouldn't that be AH?
Hmm?
Wouldn't that be AH?
Oh, that would be AH because it's the most significant byte of the 60 bits. Thank you, very good. I'm just checking to see if you guys are paying attention.
Huh? What are we talking about again?
Doesn't the word need more in it?
Hmm?
No, but you subtract 2 bytes.
1, 2, 3, 4, 5, 6, 7, 8. Okay, weird. I missed 1 0. Good catch. That's why I normally don't use binary representation. I use hexadecimal because in hexadecimal it's just 100, and it's harder to miscount by 1 bit. The other
I'm
two are
surprised you
correct.
didn't subtract 1 from 100.
I'm better than that.
You would have gotten FDF.
Okay, so this is the correct version. This is the correct version, and the right result will be as the answer. If someone uses another subtraction instruction here, then the answer will be wrong. This is the correct version.
So let's copy the correct version and make it into the incorrect version and run them both and see which is right. Yeah, just CP the file.
Oh, the other way around. I can make it wrong. Right?
But aren't you updating AX? Oh wait, never mind.
Oh, I reinitialized everything.
Yeah, I didn't catch
Yep.
that.
Okay, so let's go ahead and run this program. AS big steps.
Be right, be wrong. Can you do that in one line instead of two?
Hmm?
Your breakpoint, can you set them both on one line instead of two?
Okay.
You can't R wrong.
Oh, B wrong. Okay. I was combining the run with the setting of the breakpoint. Okay. So I run it and run from the beginning, and here we are at the first breakpoint, which is the label right. You can tell it is at the label right, and the result should be correct. What should be in AX? Now this is the other thing when you come up with your own sample program, you need to know the correct behavior of the program before you try to run it. So in this case, what should that be? If I look at AX all by itself as a decimal value, what should it be? Decimal, in using base 10.
No clue.
We have 256 minus 1 basically, which is 255. So, using the right instructions, it should be 255. And that's exactly what it is. I continue to run the program. C stands for continue, which means it will run the program until there's another breakpoint to stop it. This time it's at the wrong label. What should be in AX at this point? We'll have 255 plus 256 because the least significant bit of the most significant 8 bits is incorrect at this time. Okay, it is 1 minus 0, which means it will still be a 1. So that's why we have 9 ones consecutively, and that's 511. Okay, so let's take a look at AX again at this point, and it is wrong. It is 511. Okay. Are there any questions about this sample program? Is it okay? Self-explaining? Okay. The labels are self-explaining. Shall we move forward? We are going to move to topic number 4, which is also a good time to announce that on Thursday we'll have a practice exam. So we'll finally have practice exam number 1, which means next Thursday we'll have actual exam number 1. So I'll give you guys 1 practice test, and then you have 1 week to prepare for the actual test. So next Thursday we'll have the actual test. Yep.
So the practice exam is the same as the similar or exactly the same?
As I always say, it will be confusingly similar.
Confusing.
Yes, you will look at the question and go like, hey, that looks exactly the same as the question. Oh wait, that instruction doesn't have an L anymore. Yep.
Will the actual exam be open practice exam?
Yes. Which sometimes hurts. It does not help, it hurts because when you look at the practice exam and you look at the actual exam, they are so similar. So when you still continue to think in the format or you're still in the same line of thinking using the practice exam, sometimes you will basically overlook things that are different between the two. Yep.
Will we be writing actual code or just replacing question marks?
we'll be replacing question marks and finding out what values you have to put into certain places to make a certain flag combination happen, that sort of thing.
Cool.
Yep.
Go over the practice exam before we do the real exam.
Yes, that's the whole purpose of this Thursday. Is I will give you the questions of the practice exam. I will actually walk through the entire thing. I will answer those questions. And also show you, we'll probably, do you guys want to do it online or do you want to do it on paper?
Paper.
Let's do it in the lab online.
On paper.
If we do it online, you can look up on Google and you can look up on all the class notes and everything else. It's open book, open notes, open web, other than, not counting live communication during the test, if it is online. If it is on paper, you cannot use a computer.
I mean, can we have the paper and be on the lab? Can we have it on paper and be on the lab?
No, I want online.
Okay. We can take a vote.
I vote that we kick him
Are
out.
they different tests? Or is it the same test? Like, is the in-person one on paper easier, or are they the exact same test?
It's going to be the same.
So,
Online means you can test it. Means you can actually plug in the values and actually test to see whether it works or not. If it is on paper, you won't have a chance to test it. Yep.
Can we just, if you give us the online test, can you just give us like all day and a set time limit in which we can work, that we can do it from home or anywhere we want instead of
No,
having
this
to
is
do
a
it at school?
face-to-face class, so it will be in the same time slot as the lecture itself. Yep.
So if we're doing it online, are you still there explaining it, or are we on our own?
I will be there to clarify questions.
As a class, or so you're gonna just move the class to the lab? and
Yes,
work
I'm
on it?
moving the entire class to the lab, which will take up 2 sections. I have to clear with the lab manager first, but I think we have the space to do it. So that means the entire class will be over there, in the lab, working on the computers over there. And you will be taking the test from Moodle. Okay, Moodle has I can set it up in Moodle, and basically you just have to turn in your answers by turning in the file, just like with your homework assignment.
And then you're going over it as we do it, or we're just doing it on our own? That's
You're doing it on your own, so you guys have to do it independently.
For the practice. I'm talking about the
Oh, the practice I'm just doing in the class.
Oh, okay.
Yeah, I'm doing it in the class. I will give you the solution in the class, but you will also have your own chances offline to practice, the mechanism of turning in the answers, or going from one question to the next, that sort of thing.
So you're asking about whether we want to take the exam online? Or
Correct. Yes. Online is still proctored. It's just whether you want to use a computer to do it or do you want to do it on paper.
Okay.
Yep.
So, is the whole exam going to be on flags, or is it going to be on flags and everything else we learned? Is it going to be on just
Well, the flags and the accuracy notes are the only 2 things that are really meaningful for me to ask something about. So that's the scope of the test. Would be all the flags, addition, subtraction, and also the operands, memory addressing modes particularly. Yep.
If we do the test online, would we bring a copy of our virtual machine, or would you set us up with something?
You will bring your virtual machine. Yep. So you have to remember to bring your virtual machine. Otherwise, you cannot test. You can still turn in the file. It's just that there's no way to test whether it works or not. Yep.
Is the exam more about the theory or about the practice, like
It's practical.
practical, like
So
a
it is.
simulation
So
lab
every
or-
question looks like a miniature homework assignment.
Okay.
Yep. Mm-hmm.
So, can I bring my own laptop on the exam day, because my thing don't really work with it?
You can bring your own laptop computer, but you will only be using. You still have to be in the lab physically to take the test. Now, there's one thing. If you bring your own laptop computer, you will be relying on the Wi-Fi. If the Wi-Fi goes down, I will not be responsible for anything. Yep.
Even if you forget your virtual machine, you can still set one up in like 5 minutes in class. It takes no time.
Exactly.
And you can still
The link is
use
still there.
the lab computers to copy all your assignments to your flash drive.
Mm-hmm.
If you're going to work on your own laptop, and then just copy them back and forth.
You can
and
even
upload
watch
them
the
again.
YouTube clips, during the test.
Yes.
When's the time end?
The time limit is the same duration as the lecture, so that will be 80 minutes. 80.
Almost 20 hours of YouTube.
Time is not the issue. Whether you know the stuff or not, that's the issue. Yep.
So is it all about substituting question marks, or is it mixed up with like concepts? Are you going to ask it, describe the O flag, describe the O flag, you just question mark, guess what goes?
It's all going to be practical. In other words, I will give you a question and I say, I want this flag combination to happen, and this is a half-finished program. So I would fix one of the operands, and you can only choose something for the second operand or something along that line.
Multiple choice?
No. Open-ended questions. Yep.
So you say it's not about the time, it's only about understanding the material. I've taken tests from you in the past where even understanding the material, you can't possibly finish the test in double time.
Did you guys hear that?
That's not good.
Yep.
So is it going to be like the SAT one where you take down like a quarter of a pint and you miss it? Because I think you did that last time.
Okay, can you say it again?
I remember in the 300 class, you took out, if it was multiple choice, that you take out like a quarter of a pint.
But there won't be any multiple choice. This does not have multiple choice questions. Yep.
But if we have to just fill in the question marks, couldn't you just give us a multiple choice question for each question mark? That would be a lot easier to make sure that you don't give us
I will
anything that'll
give
take
you like
double time.
64K choices, right?
Sure.
Select one of the following, and then you have 65,000.
Or just give us like 5 choices each.
Yeah,
5
go
or
ahead.
10.
Can we please just take the vote?
Hmm?
Can we please just take the vote?
To vote your grade?
Can we vote the guy that wants to take it on
It's a
paper
popularity
off the island?
contest, right? You know, we like this guy. Okay, we'll all give him an A. Okay, well, I will construct the vote, online, so it will be anonymous, so that people don't have you don't have to identify yourself as the minority, just in case something happens, right? So we'll do it online, and you guys can vote online. I'll set it up, and then I'll.
Can you show us the results when it's done?
Trust online voting. You can't trust online voting. There's too many things that could happen.
Yeah, such as tag going in and actually altering.
Why don't you just put a hat up here at the front of the class? We all write our answer
If
down.
I'm
and
going
you
to
count them
alter
out
the
today.
results, I just don't have to ask you guys, for a vote to begin with, right? So there's no incentive for me to do anything to tweak the results of the voting. Because if I say, if I have a preference, like if I want it to be online or if I want it to be on paper, I would just do that, and you don't have a choice. So just the fact that you guys have a choice means, I can go either way. It depends on, whether you guys think that having Google and having, the website online, will help or not. In other words, of all the stuff that you have to memorize, can you remember everything? If it's on paper, it will still be open book and open notes. You will still be able to bring piles of paper, books, and whatnot into the classroom when you take the test. Yep.
Just remember, anyone who's thinking of taking paper, but if you go to the lab where there are computers, you also have calculators that you can check your binary results on a lot faster.
And you can search in a PDF. Okay, so it does make certain things a little bit faster, but at the same time, turning in your answer takes a little bit longer because now you have to upload a file instead of just writing on a piece of paper. So I would say it breaks even. Yep.
How many questions?
I have not decided yet.
Ballpark?
Ballpark?
Like ballpark?
It depends on the complexity of each question. Sometimes I make one question really long, and there's only a few. And sometimes I make easier questions, and there will be multiple questions.
Can we complicate matters further by saying that the closer the two scores are to each other, the more points that the losing team wins? Like if we vote wrong, if we vote for paper and online wins, then whoever votes paper gets extra points or something. But the closer they are to everyone getting 0 anyway. To encourage us to have to think and coordinate how to split.
That's too complicated. I cannot do it. Okay, any other questions related to the exam?
So for Thursday, for the practice exam, is that going to be in the lab or in
No, it's going to be here.
Okay.
Because I will be doing the actual the practice test. Okay, so I'll let you guys kind of think about that. Just to think about the pluses and the minuses of either approach. But the bottom line is it's going to be a practical test. In other words, you'll be debugging a program, or you'll be writing some code, or you'll be filling in the blanks, and stuff like that. Yep.
Are your tests gonna be practical tests, or are some just gonna be like hit a question that's on like the notes notes, like if we understand that, besides the
You have to be able to apply what you understand. There are a few different phases when you take a class. The first one is knowledge. Okay, I remember the definition of the zero flag. Okay, that's memorization, that's knowledge. Second thing is I understand why the definition is the way it is, because the zero flag should become a 1 when the result is a 0. That's understanding. The third one is application. Can you apply what you have learned? Okay, give me one pattern. Okay, give me one subtraction that will result in a 0, or the result in the zero flag being a 1. Give me another example where the zero flag will become a 0. That's application. So I'm testing application in my test, not just memorization, because you can always look it up. When you go to work, okay, in most cases, your boss will not say, you cannot use any books, you cannot look online, you have to do everything out of your head. I mean, I would lose a job, just on the first day, on the first hour, okay, because I cannot remember anything, because that's not what the human brain is good for, okay. So I don't want you guys to have to spend a lot of time to memorize all the stuff that we talk about in this class. On the other hand, I want you guys to at least understand the concepts and be able to apply all those concepts. That's what I'm testing for. Yep.
So we can also refer to our homework?
Yes. Your homework assignments, are as long as you bring it, it will be accessible. Since it's on Moodle, can you access your homework assignment on Moodle?
Yeah.
Oh, there you have it. So if we make the test online, all the resources that are online will be automatically be available. Yep.
You know how you went over the homework, or you kind of went over like the last homework that we did with the adding of the flags. I didn't see any answers from that homework. Like you went over it, but you never were able to give out the correct answers on how to do it, or which one.
I did. I went over the answer.
Oh yeah, never mind. I wrote them down. Never mind.
Okay. As I said, you can even watch the YouTube clips. During the test, you can get a headphone from the lab technicians and just watch the whole thing or parts of it. You can even watch a Weird Al if you want to on YouTube. That doesn't bother me. Yep.
Do we still have a homework for next week?
Um,
Or is it focused on
I probably will have one new homework on Thursday, because the homework is designed to help you understand the material. So I think it's not going to hurt. Just the duration of going through all the concepts and all the material in the class to do the homework. I think that's only going to help. Even though the homework itself is out of the scope of the exam, you will still have to understand what you have learned so far in order to do the homework. So I think it does not conflict with the exam itself. Okay. Any other questions? And don't forget, you only need 37.5% to pass with a C in this class.
Nobody wants to do that.
It's in the syllabus. Read the syllabus.
You went over it.
What?
Like, the number just doesn't make sense.
The number does not make sense.
Like
You want to make it 60%? We can do 60%.
That's fine.
60% makes no sense.
Makes sense.
As I said, I just don't ask easy questions. That's basically it. There are no fillers, in this class. Okay, so let's move on to jump instructions, because so far, what can we do? Well, let's see. We can move something around. We can copy. We can initialize. We can add. We can subtract. We can compare. We can look at the flags. That's about it. Okay, so we cannot really do anything useful. So that's why we have to start to talk about the jump instructions, because this is where we can start to implement control structures. Okay, what you understand as conditional statements or if statements in C, or for loops in C, while loops in C, do while loops in C. We cannot do any of that until we know how to deal with jump instructions. So that's why we are now moving on to talk about jump instructions. And there are several sections to this. This is the first one is unconditional jumps, which is really easy. The concept of an unconditional jump is you just tell the instruction where do you want to go, and the next instruction to execute will be the destination. Okay, so it is really easy to set up one example to show this one. When you guys took the C class, did the instructor talk about go-tos and labels? No? Okay, I can see.
He told us to never
disagreement.
use them.
Yeah, not supposed to use them anymore.
But did they talk about the concept of a go-to and a label?
Like 10
No?
seconds.
Okay, that's okay. 10 seconds, and 10 seconds is all we need to talk about the jump instruction also. Okay? The jump instruction has one single operand. Okay? JMP is the name of the instruction. It takes one single operand, which is the label of where you want to go to. That's it. Okay? So let's go ahead and take a look at the program. I'll call this JMP1 because I might have multiple jump instructions or multiple jump example programs. So let's go ahead and write a simple program to do this. Do you guys want a concise program, or do you want one that is not so concise and still illustrate the point? Let's go concise.
Does it take the label of where you want to go or the memory address of where you want to go?
It takes, okay, let me put it this way. It takes a direct operand, and the direct okay, take that back. It takes a memory operand, because you cannot jump to a register, and you cannot jump to an immediate operand. You can only jump to a memory location. So you have to specify a memory operand, and whatever that memory operand is, it will be the destination. It will go to that location next, after the jump instruction. Okay? But we're not going to do anything fancy. We'll just do something like this. Okay? In other words, we have a label here. Remember, this label is really just a symbolic name of the address of the first no-op instruction. Is that okay so far? The meaning of the label. Okay? And it just so happens that I use the same label that defines the beginning point of the entire program. Okay, I don't have to do it that way, but since someone asked for a more concise example, this one is kind of concise because I don't need to define a new label to illustrate the point. The no-op instructions really do not do anything, okay, and therefore the name, no-op means no operation. So they're basically just fillers so that we can see that, we go through these instructions, and then we get to the jump instruction itself. The jump instruction itself, as the name implies, will basically continue execution at the destination. The destination is specified by its only operand. In this case, the operand is the label start, or underscore start, which means when we execute the jump instruction, it will continue execution at this label here, which means we'll execute no op again, no op again, no op again, and then jump back to the beginning. This is an infinite loop. So are there any questions at this point about the concept of a jump instruction? Okay, if you were to write this in C, it just replace JMP with goto. Okay, that's basically what goto is in the C programming language. Yep.
You can do jump label. Can you do like jump line 3 or something like that?
No, you can only jump to a label, or you can specify the exact address to jump to. Except in that case, if you specify an address that you cannot actually jump to, then it will give you a GPF, a general protection fault or a segmentation fault. Because you're trying to execute, you're trying to continue execution at a location where you're not supposed to. Okay. But this is pretty much the simplest case of jumping. So we'll go ahead and run this program. JMP1. JMP1, list the program. I cannot put a breakpoint on line 4 because that's the first instruction, but I can certainly put a breakpoint on line 5, 6, or 7. I'll just put a breakpoint on line 7 because I know we will get there eventually. Okay, and we run the program. We are now at the jump instruction. So the question is, if I single step, where is it going to go?
Line
So
4.
we'll go to line 4. Okay, we'll go to line 4, and oh, I forgot. You cannot do it at the last instruction either. There, just restrictions. Well, let's do that. It will still do it, it's just going to complain. Okay? So with single step, because the first instruction cannot have a breakpoint, and we cannot single step the first instruction either. That's the restriction. So single step, we go to the jump instruction again. If at single step, it will give me that particular complaint, and then we go to line 5 again, line 6, line 7, and so on. So are there any questions about this program or the meaning of the jump instruction? Yep.
Say we accidentally run this program in GDB and we forget to set a breakpoint. How do we get it to stop?
Well, there are a few ways to make it to stop. You can unplug the computer. that will stop it. You can do a Control-C. Okay? If you type Control-C on the keyboard, it will stop the program on the foreground. That works for most programs in the command line mode. If that fails, because you somehow set the terminal mode to the point where Control-C is not interpreted correctly anymore, you can always open up another terminal, find out the PID or the process ID of this program, and then kill it by the PID. But for this class, I think in most cases, if you just type Control-C, it will stop it. Okay. And that's a good question because sometimes we'll forget the whole thing and we say, oh, just run the program from the command line. And as you can see, it is an infinite loop. It does not come back. So all you have to do is to type Control-C and not Control-Z. Okay. Now there's a big difference between Control-C and Control-Z when you use Linux. Control-C is, hey, program stop and abort. Okay. So it will stop and it will get out of the program. Control-Z is suspend, okay? Which means the program is still in memory. It is just paused, okay? Just think of it as the pause button. So you start the next instance, you pause it again, you start the next instance, you pause again, and before long you will have a lot of suspended programs in memory. And I can illustrate. Okay? I type Control-Z, and it will give you a different message too. It will say the program is stopped, okay? And I say, oh, okay, maybe I just did something wrong. I'll run the program again, infinite loop again, Control-Z again, okay? And I'll just do it a few times, okay? And at this point, I have 5 instances of JMP. Neither is running. None of that is running, but they're all in memory. Now, how do I know that? Because I can use PS to look at all the processes in memory at this time. Bash is basically this command line interpreter, so it has to be there. But you can also see that I have 5 instances of jump 1 because I ran it 5 times, and in each time I type Control-Z to pause the program, which means the program is still there, it is not running, it's not taking any computer processing cycle. At the same time, it is still using memory space. So at this point, you can kill them. You can say, kill.
Literally kill.
Well, there are several ways to kill too. Okay, you can kill individually, which is a hassle because because of this, you have to kill with the number, which is the PID or the process ID, or better yet, you can say kill all. Okay, if you say kill all, then you identify the program by name, and you just kill all the programs that you can kill. You can try to kill a system process; it won't let you do it. Yep.
Can you name a program Bill and run the program again?
Yes, you can. Yes.
Who's Bill?
But I think these days it should be Steve. Yeah, Bill is out of that whole business already. Because otherwise, I guess we did not do that. Okay, there are 2. Okay, when you say kill, it will send a gentle message to those programs and say, please stop. Okay? And you can say kill -9. -9 means, I'm not asking gently.
Are those threat levels from 1 to 9?
No. Unfortunately, 9 is just the number representing the kill signal. You have to take a CISP 453 to understand what that means. Yep.
For a good time, try kill-13. Sig V. That's Sig V.
Oh,
453 isn't offered any longer, correct? Sorry? 453 isn't offered any longer.
I haven't seen it for a year.
453?
I emailed Antos. I think he said it wasn't.
Oh, okay. Well, if it's not scheduled, then we have a problem. It only affects students who are transferring or planning to transfer to Sac State, I think, because Davis does not take that class anyway.
It was required for a certificate, but since it's not offered, it's not required anymore. You just petition against it.
Yeah, well, you guys have to talk to Damon to find out when that class will be offered again. That's an interesting class. That's a good class.
A fun class.
It's a fun class for sure. Okay, so are we doing okay with unconditional branches? Okay.
No.
You define a label. You say JMP to that label. When the jump instruction executes, then you will continue execution at the label. Okay? Are there any questions about the jump instruction? Kind of boring, cannot really do much by itself. So that's why we have to talk about conditional branches. Okay? So after a long discussion of the status flags, I think we spent how many weeks to talk about it? At least a week and a half or so. So we finally have some instructions that can actually make use of those flags. All the conditional branches must use one short displacement or one full displacement operand. Don't worry about it. As far as you are concerned, it is just a label. Okay? You define a label and then you use the conditional branch and say, if this flag is set or if this flag is not set, go to that label. That's basically what it means. So we have a few instructions here. JC and JB are exactly the same thing. They are synonyms of each other. This instruction means jump to the label if and only if the carry flag is set. If you have JNC or JNB, it is the opposite. Jump if and only if the carry flag is cleared. And then you have one for the O flag, one pair for the O flag, because one to jump if it is set and one to jump if it is cleared. One pair for the sign flag, one pair for the Z flag, and those are the basic ones. Yep.
If you wanted to combine those, like jump if only 0 and S, would you do jump to jump? And then that's how you
Correct. Yes, you have to do it that way. Yep. But we also have combinations. In other words, remember the L flag that we talked about earlier, the phantom flag, because it really is not a physical flag. If you look at it as a physical flag, we have JL and JNL. In other words, jump if the second operand is less than the first operand, or not. Okay. This is jump if greater than, jump if not greater than, and both of these are signed using the signed interpretation. Jump if above and jump if not above. Those are the unsigned interpretations. Okay. And I also spell out, the flag combinations. So if you want to look at, let's say JA, jump if above, okay? It is the same as jump if and only if the Z flag is a 0 and the carry flag is a 0. Well, let's see. What does that mean? Let's go to a text screen here. I know we are running out of time, but I'll do it anyway. Because it really is important to understand what is above. Okay. So let's say we have a compare instruction. Okay. Let me just give you one complete example. We'll move a 1 into EAX, and then we have compare long. Let's see here. Let's say 2 and EAX. And then we have a JA to label L1. L1 is over here. We have some instruction here, and then we have an instruction here. Okay. So this is a little bit of a program to give you an idea of what is JA, or how do we interpret JA. As it is right now, are we going to jump straight to L1 or are we going to execute a no-op instruction? Okay. So the question is jump if and only if EAX is above 2. So we are not going to jump in this case. Okay, now remember this order. I know we are running out of time, so I will talk about this again on Tuesday. There is a specific way to look at the combination of a compare instruction and a conditional branch instruction. Okay, so I will say that again, but this time I'll use a mouse pointer so that when you replay the video clip, it will be in the video clip. Okay, look at these two instructions together. What it means is jump, okay, that's what a J is. Jump if and only if EAX is above 2. Above is greater than in a unsigned interpretation. Yep.
So it'll jump if you change the 1 to like a 3 or something?
It will branch if this is a 3, yes. So this is another way, this is another place where, writing your own sample program is going to be helpful. Because you can just write a program about this size, okay, maybe a little bit longer, I think this is kind of like the minimum size to do something like this. And you can run the program. But you don't want to run the program because when you run the program using R without a breakpoint, it will just kind of zip through and can tell you there's nothing wrong with the program. So what you want to do is, you don't have to set the breakpoint on the first instruction. I don't think the move L $3 to EAX is really particularly interesting. We know what it's going to do. So you want to set the breakpoint on the second instruction, the compare instruction. And after the compare instruction, you want to look at the flags. Okay? You want to look at the flags, and then you go to the next instruction, the JA instruction. At that point, in your mind, you should know already which way it's going to go. Okay? Because this instruction says jump if EAX is greater than 2, unsigned, to L1. Okay? So if that is not the case, it will just continue with the no op instruction. If that is the case, or if EAX is in fact bigger than 2, then it will go to L1. So the next instruction, if you execute a JA instruction, you only have 2 choices left as for what is the next instruction. It can be this instruction here, the first no op, or it can be the second no op instruction because of the conditional branch. Yep.
I didn't see any jump it below options.
Because it's also JB. JB can be interpreted in either way because it both starts with a B. Jump if the borrow flag is set is exactly the same thing as saying jump if below. So if I change this one to a B, then the meaning becomes, okay, I have to keep remembering to use the mouse pointer. Jump if EAX is below 2 to L1. Or I should say jump to L1 if and only if EAX is below 2. Yep.
Go ahead. Do the jump instructions ever alter the flags, or do they just read them?
It only reads the flags, it does not change the flags. Yep.
So is above the same as greater than?
Sorry?
Above is looking at it the same as greater than?
Above is unsigned and greater than is signed.
Oh.
So that's why those two are important, because one will look at, okay, the G flag, if you look at the JG, it will look at the overflow, the sign, and also the 0 flag. If you look at the JA, it will look at the borrow or the carry flag and also the Z flag. Yep.
So if we put -3 into the first one when we did that JA, it would...
That's a good question. What do you think would happen when I change this to this? Okay, that's a very good question. I know we are running out of time, but this is still related. This is still very much related to what we talked about today. Okay, so the question is, what am I specifying as -3 here as the first operand of the move L instruction? It seems like it is signed, but it really is not, because all I'm doing here is to specify the bit pattern representing -3 to be copied to EAX. That by no means is controlling whether, okay, JB is looking at the borrow flag. So do you think the borrow flag will be set in this case when I have -3 or the binary representation of -3 subtracting 2? What do you think? The borrow flag will be cleared, okay? Because the representation of -3 is 1, 1, 1, 1, 1, 1, 1, 1, 1 all the way, and then the least significant 2 bits will be 0, 1. The representation of 2 as a binary number is going to be all zeros except the first 2 digits, or the least significant 2 digits will be 1, 0. So the answer is it's not going to generate a borrow. There's no way it's going to generate a borrow. Yep.
So, just figured out how you have to change the number. But explain what do you mean, what the negative 3 means again, because it doesn't mean...
Negative 3, okay, let me put it this way. Negative 3 is the same as 0x f f f d. Okay? It's just specifying a bit pattern. Okay, never mind, I forgot the other 16 ones. Okay? But when you look at this, they're exactly the same. The instruction is exactly the same whether you specify negative 3, 0x f f f f f f f d, or 0b 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 0 1. They're all equivalent.
You kept track of those places very good. You kept track of those places.
Yeah, that's why I'm using a virtual space here. I'm actually seeing the numbers.
You know,
Okay.
we have psych professors here.
I think psychiatrist is different from psychologist. But are we doing okay so far? I mean, this is the last thing I want you to make sure that you guys understand. Does everybody understand why this is the same as that? Okay, because that really is important. That's how you change the perspective from a C perspective to an assembly language perspective, because we are only operating on the bits. That's all we are dealing with. So I'll see you guys on Thursday. Some of you go to the lab.
Later.